Thank you all. I'm going to talk about all resolutions inference, which is a method for analysis of fMRI data. It's a collaborative effort with Jelle Groeman, Aldo Solari, who sort of invented the method, and Livio Finus, Jonathan Rosenblatt, who translated it to the fMRI realm. A common way to do cluster inference is to do fMRI inference is doing cluster inference, which we have a map of Z values, we threshold it at a certain point, and after we threshold it, we look at the remaining clusters, and we test those clusters with, for example, random field theory. And in these clusters, we want to say something about all voxels in these clusters are active, or we interpret it, in a sense, in this way. But this is not really correct, because the only thing we can say about when we find a cluster is that there is at least one voxel in this cluster that is active. This is the worst case scenario, but the place where we're at. So we know there's some activity in a cluster, but we just don't know where it is exactly. And this leads to what we call the spatial specificity paradox. My clicker. And the spatial specificity paradox is basically the larger the cluster we find, the less we know about activity within that cluster. So if we find a small cluster, we're pretty sure where the activity is. But if we find a large cluster, we're just more unsure where that activity is. So what my goal is for today is to show you a method that increases the spatial specificity of cluster inference by estimating the number of truly active voxels within a cluster. And we will do that for any cluster that we can think of, and as many times as you want, with full family-wise error control. So how are we going to do this? I'm going to show you the 4-voxel brain. This is a brain consisting of 4 voxels, where 3 of the voxels are significantly active. You can see the p-values in bold there, and you have 1 voxel that is not active, that has a larger p-value than 0.05. And this brain, we can divide this brain into all the possible subsets of these 4 voxels. So we have 3 voxel sets at the second row, 2 voxel sets, and we have 1 voxel sets. And we can describe these into a sort of hierarchical structure which shows all the subsets and the supersets and their dependencies. So what we'll do for every subset that we have, we will perform a test to see whether there is activity within that subset. And we do this with the Symes test. And the Symes test asks the question, is there at least one active voxel in subset S? And we have a null hypothesis HS, that is, there's no activity, and if we can reject the null hypothesis, we have activity in the voxel. So we do that by ordering the p-values, in this example for the entire 4-voxel brain, and we look whether there's a p-value below the line running from 0 to alpha, and alpha is our criterion at 0.05 in this case. So there is 1 point below that line, and therefore in this case we would reject the Symes test. And we can do that for all the clusters in our entire brain. So let's take the full brain that we just saw, our 4 voxels, and we can reject the Symes test for that, so we give it a green circle. We can take all the other subsets, for example, subset with voxel 2 and 4, and we can do the Symes test also. So we take the p-values, we order them, and we see whether any of those p-values are below the line. And they are not, so in this case we have to assume HS, which is our null hypothesis. There's no activity in this cluster. So we can do that for all the subsets in our 4-voxel brain, and we are left with this picture. So the green ones are the ones that we can reject, and the red triangles are the ones we cannot reject. This is, however, not corrected for family-wise error rate. So we do all these tests on subsets containing the same amount of clusters, and we have to somehow correct for the fact that we do multiple tests. We can do this in the closed testing procedure, and the closed testing procedure is pretty straightforward. We reject the local Symes test if and only if the local test is rejected, so it's the first stage, and the local test of all the supersets containing that set must also be rejected. How does that look? Take, for example, the subset of voxel 1 and 2. This is rejected, and we now need all the supersets that also contain that set, and these are above in our tree, and these are all rejected as well. So from the closed testing procedure, this hypothesis of subset with voxels 1 and 2 can be rejected. So there's activity within that cluster. We can do that also for another cluster, for example, the cluster with only voxel 2 in it. The local test is rejected, but now we look at all the supersets, and we see that one superset is not rejected by the local test, so therefore we cannot reject the hypothesis of this cluster, and therefore we have to accept the null hypothesis for this one. So we can do that for all the subsets in our 4-voxel brain, and we can see that some of them are rejected and some of them has to be accepted. So from the closed testing procedure, we can now go and calculate the proportion of active voxels within each cluster. And I will give you a lower bound estimate of the number of active voxels in that cluster. Now, how do we do that? For example, for this cluster which contains voxels 1, 2, and 3, we'll look at the subsets of those clusters, and we look at the largest subset for which HS, our null hypothesis, is not rejected. And as you can see in the lower line, you can see that only the subsets are rejected with only containing 1 voxels, and all the subsets with 2 voxels are rejected. So we know that there's at least 3 minus 1 is 2 active voxels in the brain in this subset. We can do that for another subset as well, and there we can see that if we look at the subsets, so the largest subset for which the HS is not rejected is in this case 2, because we have 2 subsets with 2 voxels in it, which have not been rejected by the closed testing procedure. So our lower bound estimate of the number of active voxels in this subset is set to 1 voxel. So for any subset in this brain, we now have a lower bound of the estimates of the number of active voxels, and because we use the closed testing procedure, we have full family-wise error control. So we can choose any cluster we want as many times as we want. We know that we won't make a false claim in 95% of the time. Okay, this works now for 4 voxels, but how about for 200,000 voxels? So for 200,000 voxels, there are 2 to the power of 200,000 possible subsets, and this is quite a lot. But due to the structure of the Symes test and the closed testing procedure, we can do this quite efficiently. So for 200,000 voxels, we can get a proportion, or our estimates, within seconds. Onto an application. So does this work in practice? We have done a no-go, go-no-go experiment in which we highlighted the no-go versus go contrast. So participants had to press a button looking at several faces, and they had to inhibit for happy faces and press a button for neutral faces and vice versa. So what we did, our input was a cluster forming threshold of Z is 3.2, and we had 9 clusters that survived with random field theory. So we won't use random field theory, we just use this to select the clusters on which we would want our estimates of the active voxels. So we just use the uncorrected p-values and the cluster masks out of those 9 clusters selected, and our confidence level was set at 95%. So we see 2 clusters, we see more clusters, but I've highlighted 2 clusters. Clusters A, which is below, which has 191 voxels, and it has a lower bound of truly active voxels of 28.5%. And our cluster B, which is at the top, had an estimated proportion of, or a lower bound estimate of the number of active voxels of 46.2%. This is quite decent, but of course we want to know where is the activity located, and what we can do, because we're in the closed testing framework, we can sort of drill down, and what we've done, we upped the threshold to Z is 4, and then we ran on the clusters that remained at Z is 4, we recalculated our lower bounds of the number of active voxels. So we can see that cluster A sort of falls apart into 3 subclusters, with the top cluster having a 65.9% lower bound estimate, cluster number 2, 23.3%, and a third remaining cluster, which is pretty small, 0% estimated lower bound of active voxels. And for cluster B, which just remained 1 cluster, but now smaller, contained only 963 voxels, and had an lower bound estimate of 85.8%. So all resolution inference will give you, in exchange for your p-values in any regions of interest, within seconds, a lower bound of the number of truly active voxels within a region for any region as many times as you want, with full family-wise error control. If you want more details, the code is available on GitHub, the paper is available on bioRxiv, and details are, of course, on the poster. Thank you very much.